So here's our starting material, here's our product, and this is a synthesis. We have to add the reagents step by step. That will take us from the starting material to the product. We can go through this together. The first step will be to number. So let's see if we can come up with some good numbers. Okay, good. I think the carbon you should have especially focused on at the start is the one you called number 2. This number 2 carbon over here is tertiary. So which of these over here is the number 2? Probably this one. It's just a guess, but the best guess is that this is the number 2 because this is tertiary over here. Okay. And then we can call the other ones 1, 3, and 4. It doesn't really matter who you call 1, who you call 3, and who you call 4 because they're all equivalent now over here. Okay, remember the whole point of the numbers is to give the same numbers to carbons in one picture that are the same as the carbons in another picture. Okay, now I would say this is a little bit tricky. I don't know, give this a couple seconds thought. Can you see any way that we can do this synthesis? I'll give you a hint, it's going to be more than one step. We have to do more than one thing. So can you see anything that would be helpful to get us from here to here?
It could proceed as it could proceed with an SN2.
Substitution.
Because you have a non-bulky base.
Right? We have a non-bulky base?
Well, I mean, you could use the non-bulky base.
Right. To do it to be a nucleophile for SN2. Okay. And maybe put the oxygen in.
Or you could, yeah, because you could use water, but it's a poor nucleophile, so you're not going to get it.
Right. Okay. Let's talk that through. Now, what you're doing here. Pardon? Yeah. Okay.
But deprotonation, but I don't think you get it.
Okay. Let's talk that through. We got some important ideas there. Now, I think what you're basically doing is you're asking, how has the starting material changed? How is the product different from the starting material? And then you're asking for a reaction that will accomplish that change. And the big thing you're noticing is that we've substituted a chlorine for an oxygen.
Correct.
The thing you're noticing is that we're putting an oxygen where the chlorine used to be. Okay, that's very good. So it's very good that you saw that we're substituting the oxygen for the chlorine. However, we've missed another big change. The other big change is, who is the chlorine attached to in the starting material?
To the number 4.
And who is the oxygen attached to in the product?
To the number 2.
So we can't just do a substitution. Because if we just do a substitution, that would just put an oxygen on the number 4. Mm-hmm. Okay. So we can't just do a simple substitution. We can't just do an SN2, because that would just put an oxygen on the number 4, when what we really need is to put an oxygen on the number 2. So it was good that you noticed that we need to replace the chlorine with the hydroxide, but we also need to notice we need to change the position of the functional group. We need to change the position of the functional group, and in particular, we need to remove the functional group from the number 4, and we need to put the functional group on the number 2. All right. And it seems like it's hard to do that because there aren't any functional groups on the number 2 yet. Okay. All right. So the way we're going to do this is, let's start with an elimination. Okay. So let's start with an elimination. Let's do an E2 reaction. So what would be a good reagent for an E2 reaction?
OH? NaOH?
Go ahead and write that down. Okay. Now, remember we want to do E2 and not SN2. So should we use something bulky or non-bulky?
bulky.
That's right. The NaOH might work, but it's not going to give you a very good yield. As we were discussing a little bit earlier, if you want to do an E2, you might as well use the bulkiest thing you can. Well, who's the bulkiest thing we could use here? Tert butyl oxide.
Okay.
So a good first step would be to use tert butyl oxide. Did you see a problem with that? Or? Okay. So let's draw the mechanism for what would happen if we use tert butyl oxide. Our next step is to draw the mechanism for the reaction between the tert butyl oxide and the starting material.
I'm having a problem with the stereochemistry, so.
Okay, what about the stereochemistry is the problem?
The invisible hydrogen, how do we know in what direction that is? It's going,
Oh, okay.
Because you have to make sure they're anti-periplanar, correct? Or not?
Yeah, let's talk about that. So I'll put this hydrogen in here. Here's the beta hydrogen. There's only one beta carbon. Is this a stereocenter?
No.
No. That's one indication that we don't have to be too careful about drawing wedges and dashes over here. So in particular, it doesn't matter whether this hydrogen starts out anti-periplanar or not. It could always rotate to be anti-periplanar. This hydrogen could always rotate to be anti-periplanar. The only time that we've seen that a hydrogen can't rotate to be anti-periplanar is when it's stuck in a ring. We saw that when you're stuck in a ring, the hydrogen can't rotate necessarily to be anti-periplanar, but hydrogens that are not in rings can basically always rotate around the single bond. And we don't even have to bother showing that rotation though, because the exact orientation of this beta carbon doesn't really matter because it's not a stereocenter. And because this is not a stereocenter, the exact orientation of the wedges and dashes doesn't matter. So we can just go ahead and draw in the hydrogen just anywhere we please and draw the mechanism for that. And then let's, down here, draw the intermediate we're going to get from that step. Good. All right, so the products from that step would look like this. And the product we're really interested in is this one. And let's keep numbering. We want to keep numbering every single picture.
Okay.
All right. All right, so yeah. In some cases, we don't need to worry about the anti-periplanar issue. Anything that is not in a ring can always rotate to be anti-periplanar.
Okay.
And we don't even have to show that rotation if this is not a stereocenter.
All right.
Now we want to ask, is there anything we could do to this to make it look like the product? And now you're going to have to reach back for another addition reaction from the last term. Because again, we need an addition. Previously, we saw, in the last problem, we saw an addition that would add a halogen. You have to ask yourself if you remember any addition reactions that would let us put an OH in here. So I don't know, do you remember any additions that we could use to put an OH in here?
H2O.
Putting in H2O, good. Now, it turns out we need a little bit more than that. So the problem here is this gives us a good nucleophile, but doesn't give us the electrophile that we need. So we need to start here with an acid like sulfuric acid. So the reagents here would be sulfuric acid and water. All right, and let's go through that mechanism. Could you tell me in words, what do you think is going to happen first here? Not sure? Okay. Well, anytime you have a strong acid, we know what's going to happen first. Anytime we have a strong acid, we have to start by protonating somebody. That's an important rule in organic chemistry. Anytime you have a strong acid, you almost always start by protonating somebody. That's actually something that you'll be able to review a little bit more in that alcohols video we were talking about. That's one of the issues we went over there, the idea of protonating things. Okay, so the fact that we have this strong acid means we have to protonate somebody.